In question 4, we're asked to find the magnitude of acceleration and the tension in the string for this system of connected particles. Important to note straight away that it's a smooth plane, so frictional force isn't acting here. So if we put in the main piece of information that we've got, we have the tension in the string, we have the acceleration in the string, and we'll assume it's moving in that direction, and we also have the weight of A acting vertically downwards. A has a mass of 5 kilograms, so that's 5g. B a mass of 9, so that's 9g. And let's not forget to put in our perpendicular and parallel components of that 5g weight, which will be 5g cos alpha and 5g sine alpha. We're now in a position to look at each particle as a separate entity and apply Newton's second law. So in the first instance, I'm going to apply Newton's second law to A, parallel to the slope, taking upwards as being positive. So we have t minus 5g sine alpha is equal to the mass times the acceleration. And then I'm going to apply Newton's second law to B, taking downwards as being positive, and we have 9g minus t is equal to 9a. Now these are connected particles by an inextensible string, and we also know that sine alpha is equal to 0.21, so I should be able to equate these two equations. In this case, I'm going to say here that t is equal to 9g minus 9a. A small rearrangement there, which will allow me to remove t from this equation. So substituting in, I can see my t is now 9g minus 9a, minus 5g times 0.21, we know that sine alpha is 0.21, is equal to 5a. Adding 9a to both sides, I can see I have 9g minus 5g times 0.21 is equal to 14a. Therefore, a is going to be equal to 9g minus 5g times 0.21 divided by 14. That gives an acceleration in this case of 5.565 meters per second every second. Once we have the acceleration, we can put that directly back into this equation we used to substitute, knowing that t is now equal to 9g minus 9a. So t is equal to 9g minus 9 lots of the 5.565. So t is equal to 38.115 newtons.